Welcome back. Can we start? So I explained you how induced EMF is generated from your DC machine. In real case, the voltage and current generated by your DC machines are not pure DC. They are AC. If they are DC, then you can't produce any voltage because the two conductors, one is a fixed conductor, one is a movable conductor. If they are not producing any force and displacements, you can't be able to produce voltage as well as when it is operating as a motor, you can't be able to have a motion. Impossible. So one has to be continuously displacement is required. So that's why in a generator, this one turn coil is rotated in the magnetic field. The conductor cuts the flux, the EMF is induced, the EMF is AC. In order to convert this guy into DC, we are using slip ring. Then we are connected to a DC loads. With this continuation, let us see how DC generator has different parts. So a simple motor, a simple DC motor. A simple DC motor, what are its parts? One is called armature, which is the rotating part. In AC machine, later lectures, I will call it as rotor. It's the same. In DC machine, armature. In AC machine, it's rotor. The next terminology is commutator. I said you use slip ring. The older machines, we use commutators. Advanced machines, we use slip rings. Now become brushless. Latest technologies. So the commutator, what is the purpose? It converts the AC to DC or DC to AC. It depends on the application of your DC machine. Then we have brushes. I showed you the brushes, X and Y, which is the output of your DC machine. One is plus, another one is minus, plus and minus. Then we have axle. What is axle? This is the axle. Shaft. There is an axle. You can have a look. This is the axle. This is your commutator. And X and Y is your brushes. Then you have an armature coil, the middle, the rotating part. A huge cylinder made of copper coil is the armature. Then we have field magnets. We call it as field winding in DC machine. In AC machine, we call it as stator. So we have field north and south. Then we have DC power supply, where I can take a DC power supply here. These 2 points, the brushes. It's clear to you? Not this one. Here I feed AC power. This is called fan motor, universal motor. I can apply AC here, AC voltage, and it start rotates. But if I want to take a DC, I have to take from here. It's clear to you? Now let us look at the how the voltages are converted through your commutator or slip ring. You can have a look. The voltage generated from your single turn of your armature coil is AC. But what happened because of these slip rings? You can have a look. The negative cycle is clipped off. Look at here. You have the negative cycle. I'm right. Plus 20 volt to minus 20 volt. Now I get only plus 90, plus 20 volt. And all the revolution between 0 to 90, 90 to 180, 180 to 270. Look at here. As I said, the output is a function of sine theta. You have to have a shift of 90 degrees. Sine 90 is the maximum. So next 90, it is maximum. Next 90 is maximum. So 90, 180, 270, plus 90. Back to again the 90 degrees. So it's a 360 revolution. You get a pulsating DC. It's not pure DC. Or it's a pure DC? No. Only the negative cycle is clipped off because of your slip ring. Still it is pulsating, I'm right. It's not pure DC. What is the pure DC? It should be straight line. I'm right. So I need a voltage something here. That is called wave shaping. The next stage in a DC machine, we are interested in improving the wave shaping. For this purpose, what I am going to do. So this is the voltage, I got it from the slip rings. You can have a look how to improve it. For that purpose, what you are going to do? I have a south pole, a north pole. An example, I'm going to take 4 coil, 4 commutators. What is the purpose of commutators? It converts AC into DC. Don't forget. Now I have 4 coil A, B, C, and D. 4 coils I have, and 4 commutators. You can have a look. A, B, C, and D. Now this is going to be rotated in anti-clockwise direction from north to south. Here is the north pole, here is the south pole. So I am rotating this direction, anti-clockwise direction. For example, now I am going to start the rotation with 4 coils, okay? When I start with the 4 coil, you can have a look. All the voltages are shifted very near to 20 volts. Okay. If you have only 1 coil, you will produce more AC. As the number of coils, as the number of commutator is increasing, you get a very flat DC. That's why if you look at this machine, you have n number of coils inside. N number of coils, I'm right? And you have almost 20 to 25 slip rings. This is commutators. The purpose of increasing the commutator and purpose of increasing number of the coil is to make your AC voltage increase. Clear to you now? So when you increase this, what happened? You are trying to tip all the AC voltages in the rotation with 360-degree angle. You clip everyone and bring up to a DC. That is the purpose of this one. That's why we are not having only one set of slip ring. So there is a calculation for this purpose. To calculate number of conductor, number of slip rings, there is a calculations. And to calculate number of brushes. We will see with the example. Now what happened? It start rotating. You can have a look. Now look at here. This is A, B, C, D is in this position. Now shifted. So B is replaced by A, C is replaced by B, D is replaced by C, and D is replaced by A. I'm start rotating. It's clear to you? Look at the location of the brushes. It was 90-degree. Now shifted to 0-degree. I'm right. X comes to 0-degree. I'm start rotating. Then again, I'm going to rotate. Keep on rotating. So what happened? At each instant, these coils will cut the flux. I'm right. Each instant, the coil will cut the flux, and each coil will start generating its own induced EMF. For example, coil A generate EA, coil B generate EB, coil C generate EC, and coil ED will generate ED. They generate its own individual induced EMF voltage according to Faraday's law of electromagnetic induction whenever they cut the flux. Now all these will be added up and you are going to take it out. Look at here. Only 2 brushes are here. Inside the conductor, many conductor. I'm right. N number of turns. But output is only 2 brushes. I'm right. So these all are collected. You can have a look. These are the rectified voltages you get. Since as increased number of coils and number of conductors, these all will be cut off. You can have a look. Then you get an induced voltage, something more equivalent to a DC. Now you got an acceptable voltage with small deviation from the rated value. This is the rated EA value, say 20. I get almost near. How it is happened? Because of all these commutators. So what I do, I come here. One commutator will cut this part. I will lose this. Another commutator will cut off this one. Another commutator. So I will get only the peaks. Here, what is the purpose of the commutator? It cut off all the AC voltages and tries to give you one unidirectional. So one instant D will cut, one instant A will cut, one instant B will cut, one instant C will cut. So all trying to cut all these lower values and you get only the peaks. That's why your induced voltage, you get something almost similar to DC. This is the simplest way I explained it. Any doubt? So if you want to have more pure DC, better than this one, what you have to do? Increase the number of coil, increase the number of commutator. Clearly? Still, I want to make it more flatter, pure DC. What I have to do? In my design, I have to increase the number of coils, increase the number of commutators. Because the commutator try to cut off all AC components. Then I get a more pure flat DC. Clearly? Can I go to the next one? This is an example of induced voltage and neutral axis. What is neutral axis, first of all? In a DC machine, so this is my DC machine. Okay, this is my DC machine. Look at here. DC, this is my DC machine. This is called neutral axis. Always in standard, the brushes will be placed along the neutral axis. What is the meaning of neutral axis? At neutral axis, you will not have any voltage or current. At neutral axis, your induced EMF or induced current is absolutely zero. There won't be any power flow. That's why we are getting this voltage. This one. This is neutral axis. Clearly, where it comes, it's very simple. For example, North Pole, here South Pole, there is an attraction, I'm right? If you keep these coil exactly 90 degree here, what happened? There is no flux interaction because the flux is traveling this direction and your coil top is here. It never going to cut your flux, I am right? If it cut the flux, EMF will induce. Here there is no flux, I am right? Obviously, the induced EMF is zero. So usually in any electrical machines, the neutral axis will be exactly at 90 degree. So we always keep this angle is your neutral axis. And usually in standard, we will place our brushes here. Why? Always from the commutator, you are getting the DC voltage before stage is AC alternating. So at any time, a short circuit can be happen within the coil because of the design. In order to avoid that problem of any short circuits, we are always keeping the brushes along the neutral axis. In the neutral axis is very safe. At every 90 degree, you get zero. This is the reason. It's clear to you? Now look at here an example. Last case we have seen 4 coil. Now we are going to see 12 coil, 12 slots and 12 commutator slots. What is slot? Before that, I want to show you this one. So we have coils. I'll show you some coils there, am right? How to mount it? I need some medium to place it, am right? This is the medium. So this is called staples. We have n number of staples like this. They mount it like this, and you get some structure like this, a cylinder. Then they will make a high pressure, temperature and pressure with impression. It becomes fixed together. They fix together with a high temperature and force. They compress with a force. Then all they will join together like this. Then they will put lamination. Why they put the lamination? To avoid any short circuits or connection between this layer and the conductors, to avoid many reasons. We'll see later. Okay. Then they create like this. Clear to you? So if you look at individual slots, this is an example where we will place our inductors. We will mount. So once something happened like this structure, we will mount it. Clear to you? Please have a look. So this is called teeth. It's like our teeth. This is called teeth, and this is called slots. This is just one single staple. Okay. You can also count a number. You can have a look. This is part one. This is just one, okay? A simple layer I'm showing you. Okay. You have to keep in order, size, design, everything. You compress at a high temperature and pressure, then you laminate. This is lamination. You can have a look. This is a lamination. Main reason it is laminated, we will discuss later, not now, and it is big confusion for you. Okay. Now let us go here to our requirements. You can have a look here. Last slide we had 4 coil. Now the number of coil is increased to 12. Here is the number 1 coil, the number 12 coil. As the coil is increased, you can have a look. Number of commutator also increases. Slip ring also increased. So slip ring or commutator also increased, but the brushes is the same, plus and minus. And this is kept in the neutral axis just to have an idea, because they will also rotate. So when it is coming at neutral axis here, the voltage to the brushes are 0 currents. So here it is 0. You can have a look. 0 voltage you are producing. Whereas the brushes are here, it's not 0. It has a polarity. But here is a plus, here is a minus. The most simplest way I'm explaining you. Most simplest way. As started rotating, you can have an example. Here each coil, for example, this coil is in neutral axis, so the voltage is 0. So this is called neutral axis. And this coil produce 7 volt, this coil produce 18 volt, and this coil produce again 18, 7, here 7, 18, and 18. When you add all these voltages, you are going to get at the terminal, which is around 70 volts. How it happens? All the voltages will not be positive. Some you already see in the structure I showed you is going to be AC. You will have somewhere plus 20, somewhere you will have minus 20, again plus 20 is a combination. And all these coil are copper coil. You know, in copper coil, the inductor, this is the inductor, you will have an internal resistance. I'm right? The internal resistance, what it will do? It will drop the current, I'm right? It resists the flow of current. So there will be a drop inside your inductor, in the conductor, each conductor. So there will be a small drop in the voltage. That's why you are getting, you can have a look, 7 volt, 10 volt, 18 volt, depends on the positions. All these voltages will be added and you are getting around 70 volt. As an example. Whereas the same location, another instant, we are looking at the coil. Somewhere this location, you can have a look, just tilted around 30 degree from the neutral axis. Now it moves here. The voltage drops to 63 volts. Why? The voltage across each coil, 12 coil, also changes and the drop increases. You lost the voltage by 7. So the brush location plays a critical role when it moves around 360 degrees because of the drop through your conductor plus the voltage created by the individual coil. There are 12 coils. As an example, we can't see inside. This is electrical machine. How I know each coil, what current is going to carry? Only I can able to see at the terminal. Am I right? Well, what happened inside is an example. We are giving an illustrative example. What can be happening inside? One coil produce 20 volts, one coil produce 7 volts. I combine all through arithmetic addition based on the polarity. Some are positive, some are negative. Finally, I added and getting at the terminal. This is an example. Any doubt? Then how to calculate the induced voltage? It can be given by the induced voltage for a lap winding is given by Z into N into 5 by 16. Where Z is the total number of conductor, phi is the flux, and N is the number of rotation of the speed of your armature. So N is the speed of your rotation of your armature, Z is the total number of conductor, and phi is your flux. So you can easily calculate what is your induced EMF at each instant. Any doubt? Just keep the formula is enough. For you, for your examination point of view, this is important. Any doubt? Can I go to the next slide? Any questions? Any questions? Next important terminology is called armature reaction. I'm going to give you very basic levels, not too much. What is armature reaction? I already explained you what is neutral axis. This is neutral axis, where your voltage and currents are zero. I already explained you. And the brushes will be placed here, X and Y. So what happened? Your armature is rotating very fast because you are talking about 3000 RPM, 1500 RPM, not one revolution per minute, something like this, moving with the hand. Very high speed. 3000, 10,000, 5,000. So this rotating part will be revolving at 1500, 3000, something, am I right? So the conductors are moving instantaneously in fraction of second. I'm right. So at the angle of neutral axis, sometimes you can have an interconnection between north and south pole. For example, here may mismatch the coils in a very simplest way. I'm talking. I'm not talking very detailed. Sometimes the coil may have the same polarity in the neutral axis and create a short circuit. Because of that, this neutral axis may be shifted from here to here, tilted. Inside the machine, we can't see it. We can't see it practically. How to see that? Because of these short circuit happen and your neutral axis is shifted either on the right hand side or left hand side. You can see a lot of spark here. So when you go to the laboratory or when you are going to a field, an offshore machine technology is working. If you are using a DC machine and you're seeing a lot of spark, what happened? Because of the shifting of your magnetic neutral axis from its original position to somewhere, because the rotor is rotating very fast, very fast, and we are unable to control the short circuit in a fraction of a second within the conductor inside, which you create a short circuit and the sparks arises exactly here. So when an electrical machine, DC machine, is producing a lot of spark, what is your first test? Okay, there is a problem in my magnetic neutral axis. How to solve it? Just push the brushes little away. So instead of placing the brushes exactly in the neutral axis, we will be keep little away. So one procedure. Another procedure, you already know these short circuit are due to magnetic effects. You create a current. For example, the armature reaction current and voltages are created in this direction, say plus to minus. It goes this direction. I know the amplitude. This amplitude, say example 5 ampere. Basic I'm talking, okay, basic values. How I can compensate this? I put another one coil. I create a current which is opposite to this one. This is coming in this direction. What happened? This is plus and this is minus, neutral. Clearly? So in an electrical machine, this is a machine, I will mount additional one more coil, second option. First option, I will shift this guy. Not exactly on the 90 degree, I will little tilt. One option to avoid armature reaction. Second option, I know what is the armature reaction current and voltage parameters. I measured it by using external equipments, voltmeter and current ammeters. Then what I do, I design another small coil, again an inductor coil, and I apply a voltage to it, small voltage. It will generate a current and voltage opposite to my armature reaction current and voltage. So what happened when I add neutralize? The resultant will become. So this coil is called compensating coil. So in a DC machine, we also use compensating coils in order to control armature reactions. So what is an armature reaction? In theoretical aspects, exactly at the 90 degree, you can have a look, two poles, the magnetic neutral axis will be at the middle, where your voltage and current is zero. But due to the fast revolution of your armature, the rotating part, it can create a short circuit at the magnetic neutral axis because two coils will get the same polarity. Circuit short, you know the meaning of short circuit. It's same polarity is short circuit. So short circuit can happen and your magnetic neutral axis can be shifted like this. Second figure. This may cause what is the problem? Continuous revolution. Short circuit happen in revolution of seconds, in fraction of second. Lot of spark will produce across your brushes. So when you are looking at an electrical DC machine, there are a lot of spark coming here. The meaning is the magnetic neutral axis shifted. Okay, how to compensate that? Is slightly tilting. You have to calculate the angle. You can be able to tilt the brush. But usually we don't do that because the standard design. How to compensate that? Use additional winding, which is called compensating winding. Design according to the power which created by the armature reaction. You put it in opposite polarity. And these two will add up and become C. So this winding is called compensating winding. So whenever you go to the companies, when you're working in the field, if there is a problem in the brushes, I mean there is a spark continuously. One problem is magnetic neutral axis is shifted. What I have to do? I have to check my compensating winding. Maybe happen damage in my compensating winding. I have to replace it. Or maybe the company with strong experience, they don't design compensating winding. Then you have to design and put it inside the machine. Third possibility, there is a compensating winding may not be connected because the company manufacturer, they are confident with the experience. Compensating winding is not required. My machine is running well, but depends on the environmental condition and continuous using of the machine. It can happen any time. Then you have to connect compensating winding inside, open the machine, and you have to connect. Clearly, any doubt? So, what are the effects? That's very important. The resultant will be the distortion of your flux produced in your armature. So your flux, which is created, for example, you have a north pole and south pole. This is your flux. Since the magnetic neutral axis is shifted somewhere here, what happened to your flux? It goes something like this. So you disturb the direction of your flux. That is not good for your DC machine. What happened? The output voltage produced will not be pure DC. Lot of distortion will create. Speed of your armature will not be unique. There will be a lot of turbulence like flight. Lot of effects will create. And the designed lifetime of your DC machine will come down. If the DC machine is designed, say example, 100 years, it will die in 10 years. And all your brushes will get damaged very easily because they are carbon material. So these all to be considered. You have to be very careful. Armature reaction. Can I go to the next one? The simplest way I explained you. Very, very simple. Now let us see the construction of your DC generator. What are its parts? I already showed you. So you can have a look. We have a field winding. So field winding will be placed at the outer surface of your DC machine. You can have a look. It has two brushes, two poles is an example. So in order to keep the poles, you have pole pieces, north pole and south pole. And there will be a coil placed in the shoe. This is called pole shoe. So for example, where I can wind, I need some space, I'm right? I need some space. The space is called pole shoe. In the pole shoe, I will keep my windings. And it will be projected as a coil piece. You can have a look. Then I use two brushes to collect the output voltages through the commutator. So commutators are here. And the fluxes will be traveling like this. You can have a look how the fluxes are traveling inside the machine. That's why the machines are covered. I will show you the next lecture. There will be a full machine. You can have a look. It is fully covered. Here I kept like this. If it is rotating at 1500 RPM, it will be flying off. Am I right? So you need a complete cover. The outer cover, we call it as yoke. So I will show you in the next class. So it's fully covered. You can have a look. It's fully covered. And how the air gaps, you can see the air gaps between your poles and the rotating part, which is armature. So this part is called field. So one set, first set is the part of your DC machine is the field set. The field set has coils, pole piece, frame, outer frame, which protects your complete electrical machines. If it is flying, it will not come out. It will be inside the machine. Then we have brushes, commutators, and armature coils. Any doubt? This is the different parts of your field. So field essentially consists of yoke, pole course and pole. Then this is an example how your 4-pole winding machine is having. You can have a poles 1, 2, 3, 4 poles. So this is north, this is south, and this is north, and this is south. It depends on the polarity. It changes. Okay. So this is an example how you can have a 4-pole machine, and this is the outer cover. You can have see this is a frame to protect your complete machine plus to hold the field winding. So field winding will be holded inside your frame. So this is a support for your poles as well as for the armature. If something happens, some mechanical construction weaks, then the rotating part can fly out. But with the outer cover, it is well protected. I already showed you, everyone, you having a armature lamination. I showed you. This is called teeth and this is the slot. This is called slot where I will keep all the copper coils. I already showed you. And when these all laminations, taper slots, press together with high temperature and pressure, you get a structure something like this. And then I place my copper coils. This is an example how you can have a cylindrical silicon steel stampings with high permeability, and why we are using lamination in order to reduce eddy current losses. So why we are putting all these laminations to avoid eddy current losses. Clearly? Then this is an example how looks your single step teeth. We are looking at here, I'm right. So you have iron teeth here, and these materials are made with a fiber slot sticks. There will be insulation. You can have a look, complete insulation, and each conductors will be placed here. And this is an example how a cross section of 4 conductors placed in a slot. You can have a look. 4 conductor, 1, 2, 3, 4, and each are insulated. Please note, you are looking like a coil here. These individual coils are laminated, insulated. Otherwise, 2 coils can touch and short circuit can happen. So these coils, please note, either on the field or inside the armature, they are completely laminated, fully laminated. It looks like a copper coil, but it's fully, if you taper with a blade something, you will get a layer. That's a complete insulation. Two purpose, avoid short circuit between the conductor, another one reduces eddy current losses. Clearly? Can I go to the next slide? Then we are going to talk about commutator. I already explained you what is a commutator. So commutator will convert your AC voltage to DC. So you can have a look. I already showed you. So this is the armature winding. You can have a look. Armature windings. I showed you only 1 turn coil with an example, but that is a machine. You have n number of turns, and all these are connected to the commutator. You can have a look. The commutator will convert all the AC into DC, and usually it is a wedge shape, a copper material with cylindrical structure. Cylindrical structure, and each commutator segment are connected to a copper strip. You can have a look, a copper strip. These are the copper strips, and these copper strips are called as riser. So each segment is combined together is called commutator. Each segment you can have a look. This is called risers. Each segments. The complete setup is commutators. As number of commutator increases, you can make your AC voltage generated in the armature more DC at the output. It's clear to you? Then this is an example of brushes. I already showed you here. This is a very small power machine. It's nothing. It's a domestic application. These are very high power application. What I'm showing you. This is very small. You have 2 brushes. So brushes. About the brushes, they are usually copper material, soft copper material. They are connected with a commutator and slip ring here, and they always touches made of a carbon material, and they have a ultra flexible copper. You can see ultra flexible copper. They are flexible, can be tangent, that can be flexibly can be rotated, and of course they can have a tangential movements. And these brushes are kept in the brush holder. So there is a brush holder. You can have a look. It is placed inside the carbon material are placed inside the brush holders along with a spring. Why you need a spring? Because it is rotating. The carbon material or wear and tear, am I right? They are not solid. They are not absolutely solid. It's like a graphite material. So the carbon material can easily damage with the friction. Am I right? They can easily damage with the friction of the rotating parts. In order to avoid that, that will be inside the spring. The spring will help the movement of the rotation. So the brushes will not soon damage. Clearly, it has a spring balance to control high speed vibrations. So we have a spring and the brushes are holded. As an example, you can see a large size machine. Now you look at a large size machine, it is not exactly 90-degree. Look at here, they get slightly tilted. This is a small power, nothing will happen. Armature reaction is very less. It's a very small horsepower machine, very low power. That's why it is exactly 90 degrees. Clearly, but it's a very high power machine. That's why it's tilted. You can see this is a complete set of your brush. And this is an example how you have brushes for a two-pole generator. So two-pole generator, you have two brushes. This is an example of six-pole generator. You have six brushes, but at the output only two, only plus and minus. I'm right. I can have only two brushes here. I can easily say which is positive or negative. But if I have six brushes, how to do that? Connect all the negative together, all the positive together, and you get two terminals. So this is an example of two-pole, two-brush construction. This is an example of six-pole generator with six brushes. It's clear to you? How to do that? Combine all the negative voltage generating coils together, positive sets all together, you get two terminals. Now here I will have only positive, here I will have only negative. So it's a connection. Can I go to the next one? This is an example how a schematic view of your armature looks. So this is an example of your 12-pole 72 coil like this machine, big machine. DC generator. So how to do the 12 poles? You can count the number of poles. It will be 12. You can see south, north, south. So if this is north, this should be south. So there is a 12 pole arrangement around your frame, which is mounted inside. And these are your coils. You can have a look. Number of coil is going to be 72 coils. Starts with 1, finishes with 72. And you have number of commutators not shown in detail. You have number of commutators and brushes here, and coils are placed here. So these are the copper coil in 72 sets of coils. You can have a look. Sets of coil. It means not only one coil, it's a number of turns. This is an example. This is an example of how an adjacent brush looks. For example, this is north pole, this part, and this is south pole. This part, say, two poles are here, and these are the coil. You can have a look. The coil is having number between end terminal is 72, starting coil is 1. So it goes like this. How you get the output? Two brushes X and Y. So the X is available exactly between 72 and 1, and the Y brush is available between 6 and 7. You take the terminal. So this is going to be plus. This is going to be the negative. Look at here. This is your neutral axis. So this is your neutral axis, because here you have 12 poles. In the beginning, we seen only two poles, north and south. So I have a neutral axis. Here 72, here we have 12 poles, am right? Obviously, it will have 12 neutral axis. Clear to you? So each cases, north and south, you can have a look. Neutral axis, neutral axis, neutral axis goes up 360. I mean the complete cylindrical structure of your DC machine. Any doubt over? Just have a look for 2 minutes. You will get some ideas. So please note, this is your brushes, and these are your coil numbers up to 72. For example, in this instant, I'm going to take this as a positive, a negative, and this is a positive output from between 72 and 1 coil and 6 and 7. This is an example how to explain what is going inside. If I show you this, what do you understand? What is the coil number? So we give some representation. We give some number to understand what is happening at this instant. This is just a pictorial representation to understand what happened inside my machine. Clearly? For example, if I give this one, how do you know? What is the coil number 1, coil number 2? No idea. I'm right. But if I give you this one, it's easy. You know the number of teeth. Say this is 1, 2, 3, you can easily calculate with one staple. When it becomes a complete cylindrical structure, it's impossible. In order to understand the concept, we are representing in a simple dimensions. Can I go to the next one? Now let us see the commutation process. You know the meaning of commutation. The process of reversal of your, what is the definition for commutation? The process of changing the polarity of your voltage and current is called commutation. So if I have plus and minus, I need to change it to minus into plus. That is called commutation process, which is happening in your slip ring. So as an example, how to look at in the point of ideal case and in case of practical. For example, we have seen a 72 coil previous slide, this model. So here I can have a coil 1, coil 2, coil 3, coil 4 until 72. For example, at the instant, my brushes are in exactly coil number 1. Then what happened? You can see here, the current comes to my coil 1 is 40 ampere. The current for the coil 1 coming from this turns is 40 ampere. So the total is going to be 80 ampere. As an example, we are studying different currents are coming to the coil. So then we have 80 ampere. It is an example. Second case, now my brushes are moving because it is rotating. I'm right. 360 degree. It's rotating. So the coil are moving. So now I move a 25%, say 25% towards 2. Exactly. This is in the middle. Now I take like 25% here. Then what happened? The current comes from the coil 1 from this side will be 60, whereas coming from the right to the left is 20 ampere, which is coming here. So now again it is 80. So if you look at the resultant, it's always constant. That's why you're getting a constant DC. The coil adjusts by itself. Sometimes one will give 40, another will give 40. Sometimes one will give 60, another will give 20. Depends on the position. Now look at here. The coil is moved exactly 50% between coil 1 and coil 2. Then I get 40 from here, 40 from here, it's 80. Now the coil move almost say 75% towards 2. Then I get 20% current from the coil 2, so 60%, and 20% current from the coil 1, then I get again 80. Last case, now the coil is completely shifted to 2. I mean the brush is shifted to 2. Here also what happened? I get 40 and 40, totally I get 80. It's an example. Don't confuse. We have n number of coils inside. How the coil adjusts different current, but at the resultant you get a constant value. It's clear to you? It's an example. So the coil will not take the same current all the instant. It depends on the rotation and the position in contact with your main poles. So these are the two main poles, north and south. Depends on its angle of rotation. That's why in the beginning I showed you in the equation. E is given by Z into N into 5 divided by 60. That is a value system. Clear? So you know the formula how to calculate Z. Z is the number of conductor. N is the speed of your rotation. And phi is your flux divided by 60. So you can easily calculate each instant what is the induced EMF in your coil. That you have. This is like something, an ideal condition. You know the meaning of ideal, which is not practical situation. What happened to the practical situation during the commutation process is an example here. So now my brushes are fully in coil 1. I got 80, but I moved only 25% to coil 2. Look at here. Here it is 75. This is 5. This is the practical cases. In practical cases, we can't say the theoretical calculation will match what we calculated. EB equal to 5 into Z into N divided by 60. That calculation will not be sufficiently validated. So in practice, this may produce around 75 amperes. You can have a look. And here it is only 5 ampere, but total is 80. So we are verifying the theoretical background, ideal background, as same as in practical cases, but see the current. It's not realistic. It will not be the same. So ideal cases, it should be 60 and 20, but in practical cases, it's 75 and 5. Similarly, if the coil is moved 50%, I mean the brush is moved 50% to the coil 2, you can have a look. 70 is coming from coil 1, 10 ampere is coming from coil 2, and you get 80. If it is moving 75% to the coil 2, the brushes, then you get 60 from coil 1, 20 from coil 2, you get 80. And this is the last case when the coil is, the brush is fully shifted to coil number 2, you get 80. So this is the practical cases. You may ask me why this has happened. This is because of armature reaction. I already explained you what is armature reaction. The magnetic neutral axis will not be fixed. In a high power, it's a small power machine, no wires. High power, megawatt capacity, very high power machines, the effect of armature reaction power is very high. As the machine increases, armature reaction power also increases. Then the value is different, right? Comparing the small machines. That cases, because of the armature reaction, all these amplitudes are varying. Clearly? But at the resultant, the beauty of the machine, we get the constant voltage. 80 or 20 volts. Clearly? Any questions? The next one, how to calculate the inductance for the commutation. Exactly how to do that. There is a formula. Voltage induced by self-inductance is given by E equal to L into delta I by delta T. What is delta I? Change in current. Delta I by delta T is nothing but rate of change of current. So what is the rate of change of current? My brush is in position 1. I am going to move to brush 2 fraction of second. Please note, I am talking in a small words or very slowly. But think about the machine. They are running at 3000 RPM, 1500 RPM. So this movement from one coil to another coil by the brush is fraction of seconds, milliseconds. You understand what I'm saying? Milliseconds. That's why you are going to calculate what is the rate of change of current, which is given by ampere per second. And you already know what is the L of your coil, which is the inductance, and E is the induced EMF. So you can be able to calculate what is E. Once you calculated E, for example, in case how to calculate the real commutation of your inductance, E equal to L into delta I by delta T. For example, I have only one coil, say 100 microhenry is your inductance. Then I can substitute L equal to 100 microhenry. And how to calculate delta I by delta T. For example, this instant, 40 ampere. So 40 ampere plus minus of minus 40 ampere divided by your time is, say, example 1.39 milliseconds. Then you know the value of time, substitute the time, substitute the ampere, you calculate what is the voltage. 5.75 volt. It's clear to you? This is the practical reasons why you are getting this shift. It's clear to you? Actually, in this case, what should be the current? 40 and 40. But what happened? 70 and 10. The reason is this one. It's clear to you? How we have calculated all this? By testing. Put the machine into the real time, test all the parameters, calculate the current and voltage by using the voltmeter and ammeter. That we calculate. This is an example. Only one coil. Listen here. This is just for one coil. Think about this machine. How many coils? 72 coils. It increases. I'm right. That's why the amplitude also increases. Can I go to the next one? Then this is the full view. With this, I stop. We'll go see some problems. So here is a cross-sectional view of your complete DC machine. Please listen. You can have a complete view. What are the parts of the machine? You can have a blower. You can have a blower. This is an additional another electrical machine we keep because you know the generators are working in Norway 100 years, 50 years, continuously 24 hours a day, in a week, month, several decades. How much heat the machine can produce? So when the heats are produced in your coil, the inductor will lose its property and weakening of inductance will create, the machine will deteriorate. I'm right. In order to avoid these problems, we are using blowers, which can blow air inside your machine, inside your, for not for small machine, big machines. You blow air and keep the coil poles cool. For this purpose, we are using a blowers, and you can have a look. This is called armature binding. You see, armature binding, laminations, armature binding. to protect the complete machine against eddy current losses and short circuit, etc. Because your poles are very close, am I right? Anytime it can get short circuited. In order to avoid that, we use armature bindings. Then you can have a look. This is called shunt pole ions. We have shunt pole ions, also sometimes called as compensating windings. We are using. Then we use shunt pole. Then we use grease fitting. You can have a look. Here we put grease fitting to avoid friction. These are mechanical parts. Bearings are there. A lot of mechanical movements are there. In order to avoid that friction, we are using grease fitting. You can have a look. And this is called eye bolt. Look at here, eye bolt. Eye bolt is used for lifting. The complete machine, I need to lift it up by another equipments. Then I can use this eye bolt, which I can lift the machine. We use also load spring. For example, this is my rotating part. I'm going to connect with external loads. The shaft can also damage with the rotation sometimes. In order to avoid any frictions within my shaft, I also connect these springs for its balance. Safeguard. So I use spring for the balance purposes. Load springs. Then motor shaft. You know what is a motor shaft? Is already I shown you. Then there are cooling fan inside. You can have a look. This is the cooling fan. It's a small machine. Cooling fan. You have a cooling because it rotates by itself. This also rotates. So it's without any huge expenses or external power, it can do it by itself because we put just a fan outside. Along with the rotation, it can generate some air and keep your machine cool. Then we are using bearings. You have here in the bearings on the external connection. You know what is the meaning of bearings? Bicycles you are using. So the same bearings will be put it here in order to ball bearings will be used. Avoid friction between your shaft and the external load for smooth. Then we use grease inside. Then this is the armature winding. You can have a look. I showed you in the machine, the armature winding. This part inside. Then we have armature winding. This is the rotating conductor. Then we have bearing retainer. So these bearing retainers are used for the protection of your armature winding. And vented covers. This is a cover, outside cover of your machine. Then we have stator foots. What is the purpose of stator foots? To rest the machine. And it avoids any vibration because machines are running at high speed. You create a lot of vibration and the vibration can affect surroundings. In order to avoid the vibration, we have foot rest. So the foot rest are used with a stator foot. Then we have interpoles. Listen here, these interpoles are technically called in DC and AC machine in order to avoid armature reaction. This is nothing but like a compensating coils. Then we have junction boxes. What is a junction box? To get the terminals, I have these cables. I need to get all this. So this machine will be fully covered. I will get only these two terminals. This is fully covered. This is open, but actually this shaft will be covered with the frame. At the end, I will have only these two terminals, fully covered. So these are used for getting junction box or used to get all the terminals. Later cases, you will be doing some experiment along with the Theresia in the lab where you can see only the terminals. That is called terminal box. Then we have brushes. I already explained you. You can have a look the brush, how it looks. And these are motor leads, lead terminals. And you can have a brush and brush holder. So brushes will be kept inside the brush holder. The carbon material will be placed inside the brush holders. Then you have solid covers to cover the machine to protection purpose. Then we have brush holder leads. We get the terminals. This is called brush holder leads. This part. Brush holder leads. Okay. Then we have brush holder insulators in order to protect that one because this machine is not insulated. For example, this is in service. I put the power. I can't touch here on that. I'm short circuited. So this will be covered with a brush holder insulators. Then we have bearings. You know the meaning of bearings. The same here you have seen. Then riser connections are shown here. What is riser? I already explained you. all the commutator sets will have individual risers. You can see the risers, each single slots. Risers, they are called risers to get the connection output to your brushes. And I already explained you what is a blower to cool the machine. So this is an example how a high power machine used in industries. Another example I showed you here from your textbook, which is 100 kilowatt, 250 volt, 1750 RPM revolution per minute, 4-volt DC generator. Then you can have an idea how big. What I have shown is nothing here practically. Any questions, any doubt about each part? I'm happy to respond to you. Any questions? With this, can we take a break for 10 minutes or later? How do you think? You need a break? Okay. Okay, we'll take a break, then we'll do some problems. So you can take a break for 15 minutes. Yeah. Next, only 4 slides finished.